this lesson about the infiltration model. And so I know that so far you already studied with the rainfall runoff models. So now we're going to study in detail on the infiltration models. So I write you here on the blackboard my email, so in case you need further information, you have questions, doubts. So on the website you will find a PowerPoint presentation that Professor Montanari prepared, and also he uploaded and handout, a word handout. So you have some materials where to study infiltration models, a couple of them which I'm going to explain today. Okay, so before starting and analyzing in detail the infiltration model, I would like to give you, let's say, a brief summary of what you already studied with Professor Montanari. So basically you studied the hydrological cycle and rainfall runoff. Modeling. So if I represent here the hydrological cycle, you will have precipitation, then if we consider the atmospheric and surface water processes, so we are above the soil, atmospheric, and surface water processes. So we have the precipitation that we may have interception from trees and plants. Then we have transpiration. We also have evaporation from water bodies. And obviously we have the surface runoff. Okay. Then if we consider the subsurface water processes, so below the ground, we have infiltration, then from the water which infiltrates into the soil, we have the subsurface runoff, and below the ground we have the aquifer, so the groundwater table here, where we can identify the groundwater flow and groundwater runoff. So basically the rainfall runoff models schematize the catchment hydrological behavior. So they provide somehow a synthetic representation of the entire hydrological cycle. Okay? And I know that you already studied 4 different types of rainfall runoff models, which are basically the rational method, the time area method, the linear reservoir, and then the hydrology. Okay? So now today, as I already said, we are going to study in detail here this part here, the infiltration. And in particular, we are going to focus on the subsurface processes. So the main motivation to study infiltration modeling is because infiltration is able to determine the amount of water which infiltrates into the soil. So one can identify and distinguish between surface and subsurface runoff. Indeed, infiltration is fundamental for agricultural purposes, but also for the determination of the surface runoff. Indeed, when you need to estimate a flood, so that the maximum discharge is a function of the rainfall, but is a function also of the soil properties. Okay, so everything is clear so far? Any doubts? Okay, so don't hesitate to stop me. Okay, so we now focus on the subsurface water process. And so, as already presented, we have the infiltration, subsurface runoff, and groundwater runoff and groundwater flow. When we talk about infiltration, we usually refer to three different items. So we need to refer to soil moisture, which is the soil water content. We need to refer to the subsurface flow, and to the groundwater flow. So basically, the soil moisture identifies the initial condition of the soil, so the amount of water which is already within the soil. And the infiltration process is a function of several features, several properties. So basically, we can say that the infiltration is a function of the condition of the soil surface. So if the soil surface is already wet or dry. Then is a function of the vegetation and soil cover. Indeed, we need to, if we have a vegetated soil, we know that vegetation intercepts water and so prevents water from infiltrating into the soil, so that the amount of subsurface runoff is smaller. And also in the case of impermeable surfaces, so let's think about the streets, so we do not have any kind of infiltration below the ground. Okay. Then also the infiltration is a function of the soil properties. Which are basically soil porosity, we have soil conductivity, and soil moisture. So basically the soil porosity is usually represented by N, which is the ratio between the total volume of voids to the total volume of soil. And usually porosity is between 0.25 and 0.4. Then we have, obviously, the voids may be filled by either water or air. Okay. Then we have the conductivity, K, which is, so we may recall the Darcy equation, where we have the flux, Q, small q, is proportional to the head loss, dH over dz, and is proportional by K, which is the conductivity, which is expressed as a length over time. And so the value of K differs between permeable and impermeable soils. Then the soil moisture, which is theta. Theta is the ratio between the water volume in the soil to the total volume. From here, theta may be equal to 0 and there is no water, so the soil is completely dry, or the maximum value is N, so the soil water content is equal to the porosity. So when theta is equal to N, here you have water everywhere that fills all the voids in the soil element. Okay, so this was somehow a background on the infiltration theory. Now I'm going to use this hydrological cycle, okay, and represent the hydrological cycle focusing on a catchment. Okay, so may I clean the blackboard here? So, if we recall the mass-water balance at the catchment scale, so we have our catchment, a river, a site. So, what I'm going to draw here refers to the water cycle. So we have the precipitation, which is so precipitation intensity or length over time, so it's the precipitation rate. Our catchment is characterized by a drainage area A, which is square length. And so from recalling this schematization, we have the precipitation rate, we have a loss, the evapotranspiration, which is a function of time as the precipitation. Then we have, recalling here the losses related to the groundwater flow, L of T. Which is, as before, a length over time. And obviously we have here the surface runoff. Expressed per unit of catchment area. So from this, we want to define the water mass balance equation. So basically study how the water storage within the catchment varies in time. So dV over dt is equal, our input is the precipitation, P as a function of time, minus our losses, which are the evapotranspiration rate, the losses related to the groundwater flow, L of T, minus the surface runoff, Q of T, where V is the water storage per unit area, so is in length. So we may assume that the water storage is given by the sum of the surface storage, so the water within rivers, ponds, plus groundwater storage. So we may express this, V is equal to Vs plus Vg. This is the surface, and this is the groundwater. Then, yes?
The surface runoff from the losses groundwater should be Q over T.
Yes, but, okay. But all these rates are expressed as a function of the drainage area. So you have the volume divided by the drainage area. So each of these quantities are length over time. So you have, we know that we have a volume of water, which is divided by the drainage area A. Okay. So here also this equation is dimensionally is length over time, because I divided all the terms in this equation by the drainage area. So it's the water mass balance equation per unit area. So we know that V, I forgot to put is a function of time, because it varies during time. So it's Vt is equal to Vs as a function of t plus Vg as a function of t. Then we may assume that during a flood, we can consider that the evapotranspiration losses are negligible, and also the groundwater losses are negligible. And so here we just simply delete these two terms, because we are considering a flood. So when we have flood, we have have that ET of T and L of T can be assumed very small compared to the water storage, the precipitation rate, and the runoff rate. So following this, now the water mass balance equation reads dV times P over dt is equal to P of T minus Q of T. And we may also substitute the two components of the water storage inside this equation and explicit this equation in terms of Q. So basically, Q of T is equal to P of T minus dVg function of T over dt minus dQs as a function of T over v. So this term here represents the effective rainfall. So the amount of rainfall which effectively contributes to the runoff. Because a fraction of the rainfall infiltrates into the soil. So the green box represents the effective precipitation. While this term here represents the infiltration. This term here outside the box is the variability in time of the water storage on the surface, so the water within rivers. And so now, so from this, so far I presented the water mass balance equation in order to define how can we analytically identify the infiltration curve within the entire ecological cycle. Okay, so now I'm on and I'm going to start and present some methods we use to model the infiltration processes. So, and in order to describe how water infiltrates and passes from the soil, from the atmosphere into the soil. So, maybe I will clean this part. So, there are three different classes of infiltration models. The first class is the physically based models. Physically based model. We have the approximate models. So basically the physically based model describes from a physical point of view the infiltration process. So using the analytical equations and describing in detail the soil properties from the physical point of view. Whereas the approximate models describe, so present an approximation of the physically based models. They are somehow, so they are still physically based, but they are more simple. They present an approximation of the description of the process. And we have then the empirical or conceptual models. So basically the focus of this lesson is on the empirical and conceptual models. But then it's better for you if you, let's say, have a background of the existing infiltration models. And so you should at least know that one of the physically based model that known is the Richards equation. And this equation describes the unsteady, unsaturated flow in a porous medium, and where this flow is a function of soil moisture, soil properties like soil water diffusivity and conductivity. So the properties I already listed before. Then in the class of the approximate models, we may recall the green ant model. And here on the empirical conceptual models, so now this class of models is divided, so is based on two different approaches. One is based on the approach which consider the storage threshold models, whereas the other one studies the infiltration threshold models. These are two approaches, also known as the first one. So when we have a storage threshold, we refer to the Dunnian approach, which is done, and infiltration threshold models refer to the Hortonian approach, so Horton models. So we have storage threshold models and infiltration threshold. So here we refer to the Dunn approach, and here to Horton approach, which I'm going to explain now. So we should consider ideatic graph, which is a representation in time of the rainfall intensity, so length over time. So we consider a rainfall event, and now I'm focusing on the storage threshold approach. also known as damming. This approach is based on the fact that water can infiltrate into the soil until the soil is saturated. So until the water fills all the voids within the soil. So it's basically when the sum of this element reaches the maximum, the available volume of voids. So, and when we represent this on the Hydrology graph, so here we have this threshold, which is given by the integral, so the sum. So basically it's the sum from I, that goes from 1 to n of ji times dt, which is equal to the storage threshold. V0 is the storage threshold. So, and this means that until this time step here, all the water infiltrates into the soil. Then from this T star, we have that the remaining water constitutes the effect of precipitation, so contributes to the surface runoff. So this part here is the effective rainfall. Then if we consider this second approach, so the infiltration threshold models. So we here represent again the Hydrology graph, so J is a length over time, which is a function of time. We have our rainfall event. And in this case, we have the infiltration threshold approach. So this means that the infiltration threshold approach, we have an infiltration threshold which identifies and distinguishes between the fraction of water which infiltrates into the soil and the fraction which constitutes the runoff. So at each time step, we have a part of rainfall which goes down deeper into the soil and a fraction which contributes to the surface runoff. So basically, we can represent this generically like this, where this part, so the integral below the green curve, represent the infiltration volume, whereas this part here is the effective rainfall. Okay, so now we are going to focus on there are several infiltration threshold models, and basically today I'm going to explain 4 different models, which are some I list here. The peak index, we have the Horton method, the constant loss rate ratio, and we have the SCS method. Okay. So we should start with the peak index method. So any questions so far? Everything is clear? Yes. So, okay. Here we are in the empirical conceptual models. Okay, we have two different approaches. The storage threshold, which is this one, and the infiltration threshold approach, which is this one. And then we have, within this class of models, 4 different types